Okay, hello everybody. It's lesson 10, projectile motion. On your lesson card, there's a starter task for you to look at. Can you complete that related to the work you should have done for lesson 9? And then we'll move on to this morning's lesson. So, our objectives for today is we're looking at projectile motion, and we're looking at the term projectile, the factors that influence the horizontal distance, the different flight paths, how we can draw free body diagrams to represent different projectiles, and this resultant force and what the resultant force means and what it looks like. So the question is, how would you describe the term projectile? What is a projectile? That's the question on your sheet. Have a think about it. So the term projectile, a projectile is a body that is launched into the air, losing contact with the ground surface. So I've got 3 examples there of projectiles that are launched into the air, losing contact with the ground surface. And on your sheet, we've also got the definition for projectile motion: the movement of a body through the air following a curved flight path under the force of gravity. Now we can this flight path by a graph of height against horizontal distance. With horizontal distance on the x-axis and height on the y-axis. The question is, what affects that horizontal distance that a projectile will travel? Have a think about it. If you can jot down any ideas that you've got on your sheet that you've been provided with, and then they are predominantly affected by speed of release, angle of release, height of release, and aerodynamic factors, the Bernoulli and the Magnus effect. Now we're going to look at all of these either in this lesson or in following lessons. So let's first of all consider the first factor, speed of release. Can you apply your knowledge of Newton's laws of motions to describe the effect of speed of release on horizontal distance covered? You need to consider which law of motion it is relating to. While we do that, let's just watch a video.
Oh my goodness.
Look at the apex 55.
Bye-bye. Bye-bye.
It does.
And it does.
World champion.
And there is your winner, Joe Miller.
Okay, so what was the golfer, what did they do to get the golf ball to travel a long distance? Well, if we think about Newton's laws of motion and we relate to the second law of motion, a body's rate of change in momentum is proportional to the size of force applied and acts in the same direction as the force applies. So the larger the force applied, the larger the speed, the velocity, the power that it is, the force that hits the golf ball, the further it will travel. So the speed at which that golf ball is hit provides greater force, and therefore the rate of change in momentum is greater in relation to the force applied. The other thing to point out is also the lever. Now I don't need to mention that in your notes now, but just think about the longer the lever, the faster the golf club will be able to be swung, and the faster the golf ball will be able to be struck. So Newton's second law of motion, can you explain why speed will affect the distance travelled? And can you add it to a practical example on your sheet? And then we've got 2 little diagrams at the bottom of the sheet when you've done that says what activity might be A and what might be B. Okay, so which projectile sporting activity could be A? So going quite high but not going very far, and which could be B? You may need to pause the video here. Okay, so that's a little diagram which could be A and which could be B. If the force applied is the same at takeoff, i.e. the speed is the same, what is the determining factor that affects the distance covered? Okay, so what determines if I've got 2 projectiles that go over a different distance, but they've had the same amount of force applied, what is the factor that affects the distance covered? And that is...
Oh my! There you go.
When analyzing Ray Allen's three-pointers, the first component to examine is launch angle. Studies have shown that the ideal release angle for a three-pointer is 48 degrees. Our analysis reveals that in the 0.73 seconds it normally takes Allen to get a shot off, he consistently creates a launch angle within just 2 degrees of ideal.
Okay, so we can actually draw a graph, and on your sheet I'd like to draw this graph to show the angle of release and the horizontal distance that is covered, and how different angles determine how far a projectile can travel. So 75 degrees, 6 degrees, 45 degrees and 30 degrees. So if you want to jot that down first of all, and then we'll describe what happens at each of these angles with the same speed for each projectile. So what would happen at 90 degrees? If I threw an object up at 90 degrees, what would happen? So it would accelerate vertically upwards, but then it would come back straight back down, so it wouldn't travel any distance. Okay, so it goes straight up and straight down. At 45 degrees, that is the optimal angle to maximum horizontal distance. Okay, so 45 degrees is the optimum angle to maximize horizontal distance. Anything above 45 degrees, so in our case the 60 degrees or the 75 degrees, the projectile reaches its peak height too quickly and rapidly returns to the ground. Okay, so it reaches its peak height too quickly and then will return to the ground. So that will mean that the horizontal distance will be less than 45. And anything less than 45 degrees, such as 30 degrees on our graph, the projectile does not achieve sufficient height to maximise flight time. And again, that would be less than 45 degrees. So if you want to, you may want to go back over the descriptions I've just given you, but to complete the boxes on your sheet to fill in that information. Okay, so what also might affect the angle of release? Some clues on the screen. So we're talking about the height of a release. So you can see the ball, it's on the ground, so the height of release is at ground level, 0. But you can see the javelin player, the hand where they throw the javelin from is above the ground, and the vaulter, their takeoff from the vault is above the ground. And the golfer, to the area that it needs to land on, is below the height of where it needs to land on. So we're on height of release now, and we can have a positive height of release or a negative release. Oops, sorry. I'm going to talk. You just go through your worksheet. So positive release height, yeah, above the landing height, and negative release height below the landing height. So we know that 45 degrees is the optimal angle of release if the release height and the landing height are equal. So that's the takeoff is going to be at the same level as the landing. However, if the height of the projectile release is higher or lower than the landing height, the optimal angle will change. So where the release height is above the landing height, which is a positive release, a relative release height, such as a javelin thrower, the optimal angle of release is less than 45 degrees because the projectile has already got an increased flight time due to the fact that it is above ground level, or it's above the area, the landing area. So because it's above it already, the optimal angle of release is less than 45 degrees. Where the release height is below the landing height, so it has a negative release height, such as the golfer in a bunker, the optimum angle of release is more than 45 degrees, because we've got to increase the angle to get it up to the level where it needs to land and beyond. Okay, and that needs to increase the flight time to overcome the obstacle. If you go to page 98, there's a little diagram that shows you this, and it also explains it a bit further. So if you'd like to look at page 98. We're not going to do the experiment because that would be something I would do in class. So we're now going to move on, once you've done that, to projectile in flight. If we look at our learning objectives, we should be able to have defined the term projectile, explain the factors that influence the horizontal distance covered by a projectile. Well, we've looked at some of those, okay, and we're going to describe and explain the flight paths of different bodies. Okay, so let's first of all think about what forces are acting on this ball at this point in time. So it's in the air. We can see the direction of motion. So we know that the forces are weight, okay, and we'll have some air resistance. Now, a true flight path of a projectile, which is unaffected by air resistance, is that of a parabola. And if you look at your sheet that says projectile in flight, there's a parabola drawn on the right hand side. Okay, and there is the parabola. As seen, a projectile in flight is affected by weight and air resistance. So we've just said that the ball is only affected by weight and air resistance. Now, depending on the dominant force, the flight path will be more or less parabolic in nature. Parabolic means it's equal. The shape on your screen is parabolic, so it is equal. Okay, so let's think about this a little bit further. So we've got weight coming down, we've got direction of motion, so the ball is going up and to the right, and there's a small air resistance. Okay, if the weight is the dominant force, which it is here, and the air resistance is small, then a parabolic flight path occurs. So in your box it says explain when a parabolic flight path will occur, including a diagram. So the diagram needs to have weight going down larger than and have a very small air resistance. Okay, and it will create a parabolic flight path, like so. We've this is the next box. We've got direction of motion again. We must always put direction of motion in. We've got our weight and we've got air resistance. So we can see that here the dominant force is air resistance, okay, and weight is a smaller force. If air resistance is the dominant force and weight is very small, then a non-parabolic flight path occurs, like so. Okay, so apply your understanding of air resistance and flight paths to describe and explain the flight paths of a shot put and a shuttlecock. So have a go at them, and then you can move on with the video and see what the answers are. So pause. So shuttlecock. Shuttlecock has a very low mass and travels at high velocities with a relatively uneven surface, which all increase air resistance. So remember, when it gets a high velocity, increases air resistance. Okay, air resistance is increased at high velocities. That's one of the factors that we learnt previously. The flight path will be non-parabolic in shape, asymmetrical about its highest point. Okay, because the air resistance is the dominant force. However, our shot put has a very high mass and travels at a low velocity with a very small frontal cross-sectional area and smooth surface, which makes air resistance negligible. The flight path will be parabolic in shape, symmetrical about its highest point. Okay, we're going to look into this a little bit more looking at how we know this. So we do this by looking at free body diagrams. And when we do, we need to make sure we understand the three phases of the motion within flight: the start of the flight, the mid-flight, and the end of the flight. So if ever you have to draw free body diagrams of projectiles, you need to make sure you can do it for these three different areas. Let's see what we know first of all. Consider a shuttlecock in flight. What happens to the weight element over the flight? Okay, does it change? What happens to the weight element? What happens to the air resistance of an object over flight? Now think about velocity here. Okay, so what happens to air resistance? What is the most dominant at the highest point? Okay, so what happens to weight? Stays the same. What happens to air resistance of an object? Well, it starts off really high and then it gets less as the velocity decreases. And what is the most dominant at the highest point? At the highest point, think about it, it will be weight. So, knowing this knowledge we've got to draw a free body diagram of the shuttle at the three phases of motion in your worksheets. And I've already drawn the three different phases of motion, and then you're going to describe what's taking place in the first box, in the second box, in the third box. Also look at the tips box at the bottom. Weight and air resistance should originate from the centre of mass. Weight should point downwards. Air resistance should project opposite to the direction of motion, or would include direction of motion. So we've got direction of motion at the top anyway. So let's try and look at these three diagrams. So the first one, weight, air resistance. Because remember, this is a shuttlecock, yeah? So air resistance, weight is small, air resistance is large. It's got an uneven surface, it's just been hit really hard, velocity is high, okay? So air resistance is much larger than weight, as the velocity of the shuttle is high as it leaves the racket. It's now mid-flight, yeah? Weight remains exactly the same. Air resistance has reduced, okay? Air resistance force has decreased as the velocity of the shuttle has reduced. It is the size of the air resistance force itself that causes the shuttle to decelerate. So it's slowing it down. At the top of the flight, okay, air resistance force is now very small as the velocity of the shuttle has slowed. The weight force has remained the same throughout and is now larger than the air resistance. Consequently, the shuttle falls vertically, resulting in a non-parabolic flight. So you can see why the flight is non-parabolic for a shuttlecock. Okay, the task now is to try and apply that on the next page. Same thing for a shot put. So you've got to draw three free body diagrams showing the force acting on the shot at the start, the middle and the end of the flight. Okay. I'm not going to go through this with you, so you've got to work it out for yourself. Think about weight. Does the weight change? Air resistance. How large is the air resistance? What type of flight path will it be, etc. Okay, so we should have done all these except for the final one. Draw the resultant force of a projectile, explaining how it affects the flight path. So parallelogram of force. To show a resultant force, or what we might call the net force acting on a projectile, a parallelogram is drawn. We're going to go through this step by step and go through it with your sheet. So the box on the right hand side is where you're going to draw the diagram, and on the left hand side with the lines is where you're going to write the description. So first of all, we've got to draw a free body diagram showing the forces of weight and air resistance. Okay, so you're going to do that. You're going to write down one, and then you're going to draw the diagram. You can see we've got a projectile, and we've got weight and air resistance. Then what we do is we add broken parallel lines to the weight and to the air resistant arrows to create the parallelogram. So we've just copied the air resistance down at the bottom of weight, and we've copied the weight from the air resistance to create our parallelogram. Okay, and then we draw a diagonal line from the origin of the weight and the air resistance to the opposite corner of the parallelogram with an arrow labelled resultant force. So that is our resultant force. That's how we draw a resultant force. There's a tip. It says in the exam, do not create a parallelogram on the same free body diagram you have drawn to show all the forces acting on a projectile. Draw a second diagram to ensure you get all the marks. So to make it clear, draw all the draw two different diagrams so it's not too confusing. Okay, so what does this resultant force represent? What do you think it actually represents? So you've got to use your knowledge of weight and air resistance and flight path. How can the resultant force provide us with information about the shape of the flight path? So the resultant force represents acceleration or deceleration. Using your knowledge of weight and air resistance and flight path, how can the resultant force provide us with information about the shape of the flight path? Okay, so we're going to look at what that is now. What will the flight paths of these objects look like? How do we know from these diagrams? We've got to think about it. So look at the resultant force and look where it's closest to. So if the resultant force is closer to the weight arrow, the force of the weight is dominant, and therefore the flight path will be more parabolic. So if the resultant force arrow is closer to the weight arrow, the force of the weight is dominant, and we know that a dominant force on a projectile will have a parabolic flight path, an equal flight path. If, however, the resultant force is closer to air resistance, the force of the air resistance is dominant, and therefore the flight path will be more non-parabolic. So here we've got on the left a diagram that represents a projectile such as a shot put, and on the right a projectile that represents an object such as a shuttlecock. And we can see that the resultant force for the diagram on the left, the green arrow is closer to the weight arrow at the bottom, and we can see that on the right the resultant force green arrow is closer to the end of the air resistance arrow. Okay, if air resistance is the dominant force, it's a non-parabolic shape. Okay, that's pretty much all of the work I'm going to be doing with you, but there is an exam question, and you've also got the mark scheme. See if you can have a go at it first without the mark scheme, and then get the mark scheme done. If you've got any questions, or if you want to send me any of your work, please do email me r.mason@brookfield.derbyshire.sch.uk. Okay, take care.